Hi Era, my name is Kuzizin and today I will be giving a brief overview to the article, namely Electrowinning coupled carbon dioxide capture with ammonia as a solvent, published by Wang et al. In 2022. So the paper introduced a new approach of capturing carbon dioxide using a process called electrowinning coupled carbon dioxide capture of ECC. Instead of relying on heat, it regenerates the solvent using electricity, which is much more suitable for locations where steam isn't available. So what makes this research important is that traditional carbon capture methods are very energy intensive, mainly due to the heating step. This new ECC method could offer more energy efficient and scalable solutions, especially in industry trying to reduce their carbon footprint and use renewable electricity. To investigate this, the researchers using thermodynamic modeling and electrochemical testing. They also built a small bench scale setup to test how zinc and ammonia systems perform under different current conditions. The key findings were very promising. The ECC system achieved low energy use between 14.7 and 36.9 kJ per mole of carbon dioxide and high Faraday efficiency up to 97%. It outperformed other metal systems like copper or nickel in terms of regeneration and speed and energy efficiency. What is also interesting is that the technology is modular and based on zinc electroplating, which is already used in industry. So the idea has potential to scale and it designed to run on electricity, which making it compatible with renewable energy sources like solar or wind.
So let me begin with the first major critique of the article by Wang et al. 2022, which is the lack of long-term stability data. The main concern here is that the study does not include any multi-cycle or extended operational testing. This leaves a significant gap in understanding the reliability of the system over time, which is essential for any practical industrial application. As outlined on the slide, the authors conducted only short-duration experiments. There is no data showing how the system performs under prolonged use. No measures of degradations, fouling, or performance drift. In fact, section 4.5 of the article completely omits cycling testing or stability analysis. This is problematic because durability is a core requirement for industrial carbon capture systems. According to the US Department of Energy 2025 guidance, technologies moving toward pilot-scale demonstrations must operate stably for at least 3 years. Additionally, over time, site reactions can alter the compositions of the electrolyte, and trace impurities could lead to performance degradation. Without examining how the system holds up under these real-world stressors, its long-term viability remains speculative. In summary, while the energy efficiency reported in the study is impressive, the lack of durability data severely limits its credibility for a large-scale or long-term deployment. Now, moving on to the second critical point, the reliance on idealized laboratory conditions and the lack of evidence supporting scalability. In the study, the experiments were conducted using simplified synthetic flue gas mixtures, specifically carbon dioxide and nitrogen, under tightly controlled lab conditions. While this setup is appropriate for early-stage testing, it does not reflect the reality of industrial emissions. Real flue gas from industrial processes such as power plants or cement factories contain a variety of impurities including sulfur dioxide, nitrogen oxide, moisture, and particulate matter. This component can interfere with the performance of electrochemical systems, potentially poisoning electrodes or clogging membranes. Moreover, the study did not simulate common industrial variations, such as changes in temperature or pressure, which would occur in practical operating environments. Another major limitation is the absence of any proposed pilot-scale configuration. There is no discussion of how the system could be integrated with existing infrastructure, such as through heat recovery or optimized gas-liquid interfaces. Lastly, the ammonia-based nature of the system introduces potential safety and regulatory challenges. These are not acknowledged or discussed in the paper, which further limits its real-world applicability. As a result, while the authors describe the system as scalable and modular, those claims are largely unsupported. Without pilot trials or field validations, the feasibilities of deploying this system on an industrial scale remains speculative.
My name is Kiran Sivakumar. I will be presenting the third critique. The third critique point focuses on the absence of a techno-economic assessment, which significantly limits the study's practical value. While the research offers promising energy efficiency results, it entirely omits any cost-related analysis. This includes capital expenditure, operational expenditure, raw material costs such as the price of zinc or membrane components, and ongoing maintenance expenses. Without an economic framework, the study cannot provide the kind of evidence needed to support investment, commercialization, or policy adoption. This significantly reduces its usefulness beyond academic interest. Instead, the article focuses only on energy metrics, estimating an energy requirement of 40.6 kilojoules per mole of carbon dioxide. However, energy consumption alone does not determine feasibility. In fact, many higher energy systems like monoethanol amine-based carbon capture remain commercially viable. This is not because of their energy performance, but because they benefit from well-established infrastructure and known operating costs. More importantly, the study does not calculate or estimate the cost per metric ton of carbon dioxide captured. This makes it impossible to evaluate how the system would perform in the context of carbon markets, subsidies, or emission trading schemes. Despite some limitations, this study makes a strong contribution to the field of electrochemical carbon dioxide capture. One of the key highlights is the use of a zinc and ammonia redox pair. This is important because it's not only relevant to industry, but it also operates with low overpotential and doesn't form stable intermediate compounds. These features help improve energy efficiency and keep the system design simple. In fact, the energy required for CO2 capture is as low as 14.7 kilojoules per mole at a current density of 100 amperes per square meter. This makes it one of the most efficient electrochemical systems available. Another big advantage is that this process runs entirely on electricity and can be easily scaled and deployed in many industries, even those without access to waste heat or steam. Since it also builds on existing knowledge from the zinc industry, it's more likely to be commercialized in the future. So overall, this zinc ammonia system stands out as a promising and practical alternative to traditional amine-based carbon dioxide capture, especially in a future where clean electricity is more common.
Next, we will be reviewing the reflections on the use of AI, as this article was done using collaboration with AI. First of all, the AI tools we utilized were OpenAI, ChatGPT, and DeepSeek. We used these AI tools in order to help us summarize the long article in order for us to fully grasp the key concept and the key findings of the article. This is time efficient and it improves our comprehension regarding the article because it helps us to simplify the complex and technical sections of the article. However, there is a limitation in using these AI tools because it requires us to manually fact check every data we got from the response, as it sometimes may generate non-accurate answers.
So, to conclude, here are the 3 key takeaways from our critique. First, this zinc and H3-based ECC system is innovative but incomplete. It offers one of the lowest energy usages for CO2 capture, outperforming conventional methods in lab settings, which is very promising for decarbonization efforts. Second, it still has limited real-world readiness. The research didn't test long-term stability, real industrial conditions, or system cost, which makes it hard to apply beyond the lab. And third, the path forward is clear. What this system needs next is pilot-scale testing, real flue gas experiments, and a complete techno-economic assessment to prove it's viable. So in summary, this study is a promising stepping stone, but turning it into a real solution depends on bridging the gap between lab innovation and industrial needs. So that is all from us. Thank you.